This video, we're going to be talking about the graph of cosecant and some transformations of that. Again, we're going to be using the Desmos graphing calculator to graph these functions to show you the transformations. You should also be able to do this on your graphing calculator, and you should be able to do this by hand. So let's go ahead and talk about the cosecant graph. Let's graph it at the same time with the function that it's the reciprocal of. And there it is that you can see that the maximums of sine happen at the local minimum of cosecant and the local minimum of sine happens at the local maximum of cosecant, that everything between 0 and 1 becomes a point that's greater than 1 when I take the reciprocal, and everything between 0 and -1 becomes a point that is less than -1. There are no points between -1 and 1 for cosecant. That's very important. So, all right, let's get rid of that sine function there. And let's get rid of the table and let's start graphing some transformations. There's lots of examples here, and I also want to show you one that we showed you in the last video as well that looked like it was a secant graph with the transformations, but it really turned out to basically be a cosecant graph because of some identities, and we could rewrite it. But let's look first at this horizontal transformation of pi over 6 to the right. And there it is that our points have shifted by pi over 6. Our asymptotes have shifted by pi over 6. So instead of our asymptote being at 0, it's at pi over 6. And then our next one is at 7 pi over 6, and then 13 pi over 6, and so on. So, and instead of our minimums here being at pi over 2, it's not now pi over 2 plus pi over 6. Is 6 pi plus 2 pi over 12. No, is 3 pi plus pi over 6. Sorry, is 4 pi over 6 is 2 pi over 3. There we go. Started making a bigger denominator than I needed to. All right, so that's the first one. We graphed that secant function in the last video, so I'm not going to do that again. Now we're going to do a reflection across the x-axis. You can see that where it had pi over 2 positive 1 and gone up, now it's pi over 2 negative 1 and is going down. Where it was 3 pi over 2 negative 1 going down, now it's 3 pi over 2 1 and headed up. And so all of the y values became the opposite sign, but the period didn't change. It didn't shift at all, up or down, left or right. So there it is. Now we're going to have a horizontal compression of 1/2. We're going to put in here, and I'm going to get rid of this negative. So when I do that, now everything is, I'm sorry, I said horizontal compression, I meant horizontal stretch. That 1/2 is going to do the opposite of what it looks like. So it's actually going to slow the horizontal velocity down by 1/2, which makes it take twice as long to get to the same y value. So it stretches it out. So the period is now going to be 4 pi, and each of these loops here is going to be 2 pi. So I go from 0 to 2 pi, and then from 2 pi to 4 pi, then from 4 pi to 6 pi, and so on. So instead of that minimum being at pi over 2, now it's at pi. Instead of this maximum being at 3 pi over 2, now it's at 3 pi, and so on. You get the idea that every x value has doubled and the y values have stayed the same. Now let's take this graph that we just made and let's multiply it by 3, and you'll see that where it's pi 1, it's going to go up to pi 3, where it's negative pi negative 1, it's going to go down to negative pi negative 3. I'm just going to stick that 3 in front of it, and there it is. Nothing has changed as far as the period, but the range has changed here. So now the graph stays between negative 3 and 3 because it's now related to y equals 3 sine of 1/2 x. So it's the reciprocal of that function, or yeah. So there you go. Leave the 3 as the multiplier alone, but the cosecant function is the reciprocal of the sine function that's there. Just leave the 3 as the constant multiplier because that's how much it had to get stretched out. Don't take the reciprocal of the 3. All right, now we're going to look at 2 cosecant of 6x, and this is going to be horizontal compression. So I'm going to have to zoom in here to see this one cycle, and so it had been at pi over 2. Now it's going to be at pi over 12, and then again at pi over 4. And so you can see that this is happening every 4 pi over 12, which is pi over 3, which is 6 times as fast as we would have expected. 6 times faster than we would have expected. And this range is now between negative 2 and 2 because of this multiplier of 2. Right, let's make this a negative 2 cosecant of x plus pi over 4. And we're going to have to zoom back out a little bit. Now it's shifted pi over 4 to the left. It's been reflected across the x-axis, and it's been stretched by 2 so that it's going to stay between negative 2 and 2 for the y values. And you can see that, and you can see that the minimums and maximums here, now they're still 2 pi apart from one another like we would expect. 8 pi over 4 is 2 pi. So there's one of those key points every pi units. There's also going to be an asymptote every pi units. So there's going to be halfway between these. So that's going to be at 3 pi over 4, and then at negative pi over 4. So every 4 pi over 4, or every pi, there is a asymptote. The first one's at negative pi over 4, then 3 pi over 4, then 7 pi over 4, and so on. Number 20 is the one that we already graphed in the last video because it's written as a secant function, but I told you it's really a cosecant function in disguise, and I wanted to show you that now that you've seen a cosecant function, that if we write 3 secant of x minus pi over 2, you can really see that that looks more like a cosecant function with its asymptotes at 0 and pi and 2 pi, which are the zeros of sine, not the zeros of cosine. And it's got its range from negative 3 to 3. And it's got these high and low points every pi unit, starting at negative pi over 2, pi over 2, 3 pi over 2, and so on, which looks like a regular old cosecant function that's just been multiplied by 3. And I did all the math in the last video to prove that to you, so I'm not going to do that again. I just put the note over here that this is a cosecant function because of the even-odd identities and the complementary angle theorem, which we talked about last time. So let's move on here. Cosecant of, this one's pretty tricky, pi x over 5 plus 3 pi over 5. So this one has something that we're going to call phase shift, and we're going to talk about that in one of the next videos that we're going to do. We haven't talked about phase shift yet. but phase shift is something we have to calculate when we have both a multiplier in front of x and we have a number added or subtracted inside here with the function, and it's any trigonometric function: sine, cosine, tangent, cotangent, secant, cosecant, any of the six of them. So let's go ahead and look and see how much it was shifted. Normally we would have the asymptote at 0. Now the asymptote appears to be at, that's hard to tell. Let's figure that out. So the asymptote is halfway between negative 0.5 and 4.5. So the asymptote is going to be at 2. And then there's going to be another asymptote at 7. So every 5 units, there's going to be an asymptote. So at 2, then 7, and negative 3, and so on are my vertical asymptotes here. X equals, and then we have mins, local mins at negative 0.5 plus or minus 10. And we have local maxes at 4.5 plus or minus 10. And our range, our domain is going to be x is not equal to where those vertical asymptotes are. Our range is going to be from -1, y is less than or equal to -1, or y is greater than or equal to 1. Our regular range of cosecant. You can go ahead though and graph that. That's going to be, notice that the teacher here didn't put any pi's on the scale for that reason, because your asymptotes, your wavelength or your period, all of them, the pi is gone because of that multiplier of pi over 5 right there. So the graph has been shifted and it has been pi over 5 is less than 1, so it's been expanded out a little bit. All right, that is it. Yep, that's it for this video. We'll come back next time and we'll talk about some other things that have to do with periodic functions. And then that will be the end of this chapter. So see you for the next videos.